Oh, okay, that's nice. Thanks. Okay, so thanks the organizers for the invitation. So I'll speak about the beginning of my PhD work that I do with my advisors, Camille Laurent-Jangou and Vladimir Salnikov. So it's based, the talk is based on the following preprint. And I'll write the plan of the talk right now. So it will be a talk, so I'll try to stay elementary. It's a talk motivated by some theoretical mechanics and numerical analysis. It will be a talk about differential geometry, and I explain the link and the motivation later on. So let's write the plan. So I'll explain what's the principle of geometric integrators. And then we'll just do a bit of symplectic geometry. So smooth families of Lagrangian bisections. By the way, don't hesitate to complain about my writing. I know some people can't read me, so please ask questions. Okay, the main tool of the talk, the main geometric object is symplectic groupoids. So I don't quite know who of you in the audience are familiar with it. So we'll see that later. And the main theorem is about an equation that I called Hamilton-Jacobi. But it's not the one of classical mechanics, although it lies on the same principle. Maybe I'll say a word about this as well. Part 4 is about numerical consequences, but I mostly want to discuss math here and not numerical analysis. I think it's not quite the place. And here I explain what is the Magnus Formula and how it interacts with all the rest. And I'll finish with some open problems. Okay. So what are geometric integrators? So in physics, when you start with an equation, it often, so the resulting dynamical system often verifies some geometric properties, got some geometric invariance, and they are destroyed by naive numerical methods in general. So geometric integrators are just the construction of numerical scheme that preserve the geometric invariance of the continuous solution you try to discretize or approximate. So historically, it began with symplectic integrators in the 50s. So people started having computers and doing some long-run simulations for like celestial mechanics or Hamiltonian dynamics on symplectic manifolds. And it turned out, so some engineers noticed that it works much better when the numerical scheme preserves the symplectic form of the system. So it started there, and then geometric integrators expanded in the whole literature. So in the 60s, people started using it to molecular dynamics, for instance. Also in fluid mechanics, but this is infinite dimensional setting, so I'll maybe say a word here. And in general, can be phrased like that. So geometric integrators are, the aim of geometric integrators are to find some family of automorphism of a manifold that preserve the geometric structure of it. Okay, and we'll do that for Poisson integrators. So I start with a Poisson manifold and a Hamiltonian. I take its flow at time t. It verifies three important geometric properties. At first, well, it is Poisson. Second property, that for all x, the image of x by the flow belong to the symplectic leaf of the point, okay? And the third one is that it preserves the Hamiltonian, of course. Okay, so Poisson integrators should verify something like that. Okay, and in general, it's a hard question to build geometric integrators, especially if you have singular foliations in the game. Why? Because numerical errors behave really bad with the singularity of the phase space. Okay, so my favorite example is foliation of R3 in concentric spheres. Okay. So what will happen if you try to do some numerical simulations with a naive numerical methods? So if you start at the singularity of the system, which is a fixed point of the dynamic, you'll stay at the fixed point, it's no problem. But if you start close to the singularity, with the numerical errors on the long run, what may happen is that you end up at the fixed point of the dynamic. And then you totally destroy the geometry of the system, which is the counterpart, the mathematical counterpart of the physics of the equation. So you don't want to do that. And that's why we'd like to build some robust methods. And there is some geometry behind that I will explain now. So you see, the main issue is the singularity of the foliation, and it took me a while actually to understand it's rather natural to use symplectic groupoids of a Poisson structure to deal with this issue, because it's geometric objects that desingularize the foliation. So at the end, it's really natural. Okay, so let's start the talk. It's an integrator is a numerical scheme. Yes. Yes. An algorithm. Right. Okay, so let's start with a symplectic manifold. And we'll study smooth families of Lagrangian submanifold of V. So let's explain what this is. Okay, take a small real interval that contains 0. So L is the smooth family of Lagrangian submanifold. Smooth family of Lagrangian submanifold if, well, LT is Lagrangian. For LT. And what could be a smoothness notion for this kind of object? So you look at this space. Okay, this surject over I, and you ask this map to be a submersion. Okay, so with this notion of smoothness, okay, so L0 is here, and then you have LT like this. It can cross this as well. With this notion, we have the existence of so-called L path. An L path at X in V. If gamma is a path in V such that gamma of T belong to LT for all T. Okay? And with those paths, we'll be able to, so gamma T is here. So mark it exists. And the thing is, since the normal bundle of LT is isomorphic by the symplectic form to the cotangent bundle of LT, we have small proposition that says that gamma induces a covector at gamma of T on LT. And also, actually, this covector doesn't depend on the choice of gamma. So that's nice. Oh, it's a covector defined? So you're here. Take the derivative of gamma, and you project it on the normal bundle, and then you use the symplectic form to get a covector. The third point is Right, so if I take another one, then the difference of the two derivatives will vanish when I project them on the normal bundle. Absolutely, absolutely. 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 Yeah, thanks. Also, one can make x vary, and so it glues to a smooth family of closed one form. The closeness comes from the Lagrangian property of LT. I call them omega t, which is here. Okay. So let's sketch some examples. Let's do 3 examples, actually, that we'll need later on. The first one, that you take the cotangent bundle of configuration space with the canonical symplectic form, and then smooth families of Lagrangian submanifolds are given by, some of them are given by graphs of closed one forms on the base. So we take eta of t, and then this is smooth families of Lagrangian submanifold, smooth families of Lagrangian submanifold. And okay, so I forgot to say, we'll call those eta of t variation forms. Kind of a differential calculus on Lagrangian submanifold. So then eta of t, so eta of t will be like pull backward of the time differential of the form. Okay. Yes, it's tau restricted to LT. Yeah. Second source of examples are Hamiltonian flaws. So now I take a Hamiltonian H, and I set LT equal flow of H at time t of L0. L0 some Lagrangian submanifold. And then, so let's not care about completeness of, just assume it exists, or it's local, whatever you want. Then eta of t is just the H restricted to LT. Okay, the H is a one form on V, and it's all right. Third example, I take a symplectomorphism from V to W, and then I take L, the smooth families of Lagrangian submanifold, and I set L tilde the image of L by psi, and then the variation forms of L tilde will be related to the one of L by psi. Okay, so that will need, so this is in a general symplectic manifold, and now we do that in symplectic groupoids for particular Lagrangian submanifolds that are bisections. So this is the second point. Yes. So I really don't want to define Lie groupoids. Should I do it, or I don't have time for that? Yes, I agree. Okay, so I just state that yes. You know it. So let's say that symplectic groupoid is a Lie groupoid with a symplectic form on the space of arrows. The symplectic groupoid if the graph of the product is Lagrangian. Yes, sure. The graph of the product is Lagrangian. In G times G times G bar, where here we put the symplectic form on G, here again, and here minus the symplectic form. So maybe phrased like that. So at the end, it's just a symplectic manifold with the symplectic form being multiplicative, okay? Right, and so proposition. It exists a unique Poisson structure on the base M such that if I call alpha the source and beta the target, but whatever, this is Poisson. Okay. The way back is local. So if I have a Poisson manifold, I cannot always find a symplectic groupoid integrating it, but I can find a local one. So I don't want to say too much about this. It will be all right anyway. And here I can give some examples. So if I take the pair groupoid, with this symplectic form. So the first omega is on the first factor and the second one is on the second factor. Then it integrates the symplectic manifold seen as a Poisson manifold. The cotangent bundle of a Lie group with the canonical symplectic form integrates the canonical Poisson structure on the dual of the Lie algebra. And cotangent bundle with source and target given by the cotangent projection integrate the zero Poisson structure. Okay. Now there is an important statement given by Einstein. Okay. I'll define bisections. The Lagrangian submanifolds of the first part will be, in the present case, specified as being bisections, which means that the source restricted to L is a diffeomorphism. And L is Lagrangian. And the proposition, while it's Weinstein, Coast, and Dazor in 1989, that this proposition states that if I have a Lagrangian bisection, I have a Poisson automorphism on the base induced by it. Okay, so alpha restricted to L is a diffeomorphism. I can invert it and then project again by the target. And this is Poisson and sends a symplectic leaf to itself. So you see, we're getting closer to the properties of Hamiltonian flow. Now the question is, what families of Lagrangian bisection will induce the flow of H on the base? So the answer is quite simple. So one may take LT equal the flow of alpha star of H, starting from the base. But this is actually not satisfying. Why? Because what you want to find is the flow of H. So you basically replaced the flow of H by the flow of something else. But one like to have something better than this, or at least, so this LT is too complicated to compute this way. A much better approach is the variation forms we just computed, and it works with the following lemma. So there is a canonical one-to-one correspondence between smooth families of Lagrangian bisections on a symplectic groupoid. And two pairs made of L0 Lagrangian bisection and a smooth family of closed one forms on the base. Okay. And we'll use this lemma for the third part, which is precisely the Hamilton equation, Hamilton-Jacobi equation I built on symplectic groupoids. So for that, we need another statement, again Weinstein, that says that since the base is Lagrangian in the symplectic groupoids, the space of arrows locally embeds in the cotangent bundle of the base, symplectomorphically. Okay, this is in the neighborhood of M. And so from now on, we can assume G embeds in T star M. So now, we'd like to remember, we look for Lagrangian bisections that are of this form, but in the cotangent bundle of the base, we have a bunch of Lagrangian submanifolds that are given by graph of closed one form or even exact one forms. So look for ST such that the following equality holds. And by using what we have here in the lemma, so here we'll get the alpha star of H restricted to graph of DST. And here we'll get this equality. And so by reversing everything, we get the following equation. Okay, also one can see that S0 equals 0. So there is a time-dependent constant here that I remove. I call this equation Hamilton-Jacobi equation. On a symplectic groupoid. So now there is a theorem that says, so first, this equation always has a solution, at least for small t. And 2, if S is a solution, well, the flow of H is given by this. Okay, so yes, ST goes from the base to R. And it's smooth with respect to the parameter. It's clear? Yeah, it's a smooth function with a smooth parameter, so I can differentiate with respect to t. Right. So this is in G, which is in T star M, and this is the graph of one form on the base. Okay. Yes. Yes, by restricting the neighborhood and doing some other trick, one can get the canonical symplectic form. Okay. So a first remark is that one can actually compute terms by terms this ST by writing it as a formal series. S1 will be H, S2 will be alpha star of H, star of H. So those are the Poisson brackets of the canonical symplectic form. And one can keep on. Sorry. Up. So in general, the ith term will be some iterated brackets of H and Sj for j smaller than I with some rational coefficients. I can keep on. So we have recursive relation between Si plus 1 and all the terms before. So it's actually really easy to compute. Okay, and this allows to, so what does it mean geometrically? ST is kind of a transform of the Hamiltonian, and it kind of differentiates the Hamiltonian on the base. Now I can take this star equation and I decide that I solve it, but up to some order. So I will truncate ST at some order K. And thanks to this proposition, I'll get a family of Poisson automorphism that sends one symplectic leaf to itself and that will approximate the Hamiltonian flow at the order where I truncated this transform of H. And this is exactly the numerical consequence we are interested in, because it will give some Poisson integrators of the Hamiltonian system we are interested in. So this is the fourth part. So the proposition. Okay, so we have an equality of diffeomorphism in the sense of formal series. And the second point is that it not only approximates the Hamiltonian flow, but it approximates it in the category of Hamiltonian flow itself. So I claim this is again a Hamiltonian flow, but for a time-dependent one that approximates H. There is an explicit formula for this non-autonomous Hamiltonian. Okay. Yeah, exactly. Exactly. So now maybe I can show some numerical simulations. So I just 1 minute? 4. Okay, so maybe I won't show some numerical simulations. I'll just to say it works, I just programmed it for the rigid body, and it preserves the theory of the dynamical system, while some Runge-Kutta methods doesn't, for instance. It destroys the topology of the orbit. So we are left with time-dependent Hamiltonian, and there is a Magnus formula that can transform time-dependent Hamiltonian to autonomous one with a parameter, and that allows to recall to recover the flow of H epsilon, but with an autonomous Hamiltonian. So we get back the symmetries of it, like the preservation of energy, for instance. So if I have 4 minutes, maybe I don't detail it. Maybe I spend the last minutes to talk about the 6 parts, which are open problems. So one question is, can we do that for Dirac structures, actually? So there is a theorem from Bernstein, Zhu, Weinstein, and Feinig that says Dirac structures integrate to presymplectic groupoids. And here, we use the symplectic groupoid of a Poisson structure and the Lagrangian bisection of it to build some discrete dynamical system. So we should be able to do the same for Dirac structure. Right, there is still a notion of Hamiltonian dynamical system on a Dirac structure, but this doesn't work anymore because this isomorphism here doesn't hold, but still maximally isotropic bisections of a presymplectic groupoid give some Dirac automorphism. So there should be a way, but I don't know how it works. And also, how about field theory? And so there is there are a lot of equations coming from fluid mechanics. For instance, equation of a barotropic fluid, which is like compressible Euler equation. This equation is really hard to simulate in numerical analysis, and maybe constructing some Poisson numerical scheme with this procedure will furnish some robust scheme, but it's not clear how it works. numerically. So okay, I think.
So you don't want to show this?
If I can, I do. It's like the time of dropping down the screen. Okay. Plus, it's nice. Oh yeah, I need to. Oh, thanks. And okay, so yeah, I did that for the rigid body. So the rigid body is on the dual of Lie algebra. So the symplectic groupoid is well known. Oh yeah. And so yeah, that's typically what happens. So what happens with traditional methods when you have like a periodic orbit, you'll start at a point and it will do some error that doesn't compensate, and the long run it's like it's a nonsense simulation. While with our methods, since the discrete trajectory is again Hamiltonian for a closed Hamiltonian, it actually oscillates around the orbits. And that's why the topology is preserved. It's the momentum. Right, so at the beginning, you're here, but H is G invariant. What you get is dynamical system on G star, and you recover the whole motion by translating on the. What? Yeah. So it's yeah. So yeah, this is the equation. So by choosing some metric, one can identify G star with G, and then the Hamiltonian is the following. So this is the inertia tensor. So it's a symmetric positive definite matrix. Okay. Okay. What is the Magnus Formula? It also makes use of iterated brackets, but of the Poisson structure on the base. I should erase somewhere. Oh yeah. So, thank you. We start with a non-autonomous Hamiltonian, and then you consider it as a formal series. And we'll write the Magnus series of H this way, and it's defined as it's a formal series with coefficients in the smooth functions, such that the first term is 0, and then it verifies a differential equation. How is it? Bernoulli numbers appear here. It's something like this. Right. And the theorem is that, so you start with a Hamiltonian, non-autonomous Hamiltonian, and you get a formal series. And the thing is, formally, the flow of the Magnus series of H is parameter epsilon is equal to the flow at time epsilon of the non-autonomous Hamiltonian. And even better, so if you truncate the Magnus series at order k, write it this way, then the flow of the Magnus series will equal the flow of the autonomous Hamiltonian at order k. It's epsilon here. And I think it's k minus 1. Let me think. Yes. And so that's quite practical because now you really know what you compute when you solve Hamilton-Jacobi at order k. Then you can take the Magnus series of the time-dependent Hamiltonian. You follow the flow to, and you know what Hamiltonian trajectory you computed. Although the Magnus series doesn't always converge, so it's a formal result.